So thank you very much. So the main focus of this talk is code-based cryptography, and in particular, a mechanism-like scheme based on some rank metric codes, which are Gabidulin codes. This scheme is called GPT from the name of the three authors, Gabidulin, Paramonov, and Trechakov. And it was attacked and repaired many times. We'll see together the last attack due to Overbeck in 2008. So there are several techniques to repair these kind of systems. We'll focus on one on that, which consists in replacing the underlying code with another family of codes. And this is what Puchinger, Renner, and Bakterze did in 2018. So they proposed to replace Gabidulin codes with Twisted Gabidulin codes. So the correspondence scheme, we will call the correspondence scheme Twisted GPT. But this proposal had several issues. The first one is that it was only partial in the sense that they didn't provide any decoder, and in particular any decoder correcting up to the alpha of the minimum distance of the code. And we will see that Twisted GPT is resistant just to a specific choice of parameters of the Overbeck's attack and not to the general version of this attack. So the contributions of our work consist in, first, we discuss a decoding algorithm for Gabidulin codes, which can be adapted also for their twisted version. We will see that for the first class of codes, we can correct up to the alpha of the minimum distance, while for the second class, we can correct less. And we do an important remark. We basically observe that these codes can be decoded just knowing a generator matrix of this code. This is something which is important, especially for the cryptanalysis and for the Overbeck's attack. And this is something that we could do because we are in the rank matrix setting. And another contribution is that we revisit and extend the Overbeck's attack, and we apply either the classic version and our extended version to the Twisted GPT scheme. Okay, so let's start by talking about rank metric codes and then Gabidulin codes. So the main idea is that we can identify any vector in FQ to the m to the n as a matrix with coefficients in FQ by just choosing a basis of FQ to the m and then considering any component of the vector and developing any component as a linear combination of the elements of the basis. We then write all the coefficients of these linear components as column of a matrix. So in this way, we get a matrix with coefficients in FQ. And so this allows us to define the rank of a vector, which is the rank of the correspondent matrix, and the distance, the rank distance between two vectors, which is just the rank of the difference of these two vectors. And the rank metric code is an FQ to the m subspace of FQ to the m to the n, where the distance or the minimum distance of these codes is the minimum rank of all its non-zero code words. So in this talk, I'll talk a lot about this operator, the Q-sum operator, which will be central for the Overbeck's attack. So basically, we consider code words of a rank metric code, and we denote C to the I as the code word obtained by just applying the Frobenius operator to all the components of the code word. So in this way, we get code words of capital C to the I codes. And the Q-sum operator is just the sum of all these codes that we get. So if G is a generator matrix of our code C, then we denote lambda I of G, a generator matrix of the Q-sum operator applied to the code C, which is just obtained by considering all the generator matrices of all the codes that we get by elevating to the power Q of Q. Gabidulin codes are obtained by considering Q polynomials or linearized polynomials. And in particular, so a Q polynomial of degree D, of Q degree D, is a linear combination of the so-called Q monomials, which are obtained in this way, just considering the power Q of monomials. And Gabidulin codes are just obtained by evaluating Q polynomials of bounded degrees at the components of a vector, which is called evaluation sequence. And you can see the similarity with rank metrics with Reed-Solomon codes in Hamming metric, because Reed-Solomon codes are evaluations of polynomials of bounded degrees. Here we have evaluations of Q polynomials of bounded Q degrees. And a generator matrix of Gabidulin code is what we call a Moore matrix. So it's a matrix of this form here, where you consider the Q powers of the evaluation sequence. If we apply the Q-sum operator to a Gabidulin code, we get another Gabidulin code. And this is a very important property, which is central for the Overbeck's attack. And so keep it in mind. And in particular, the dimension of the obtained Gabidulin code is the minimum between k plus I and n. Usually we choose I, for which this dimension is exactly k plus I. So the first contribution that we did, we introduced a decoding algorithm which derives from the Welsh-Bellecamp technique for decoding Reed-Solomon codes. And we observed that thanks to this algorithm, we can decode the codes without knowing the evaluation sequence. It just suffices to know a generator matrix of this code. And we will see that this will be important for the Overbeck's attack later. OK, so let's now talk about the GPT system. So we have, it is a code-based scheme. It's a McEliece-like scheme. We have two keys. A private key, which consists of a generator matrix of a Gabidulin code. So you can consider, for example, a Moore matrix. Then we have S, which is the so-called row scrambler. It's a random invertible matrix with coefficients in FQ to the M. And then we have the column scrambler, which is a matrix, a random matrix, invertible matrix, I miss invertible, with coefficients in FQ. And the public key is obtained by multiplying the row scrambler with the concatenation of the distortion matrix, which is a random matrix with coefficients in FQ to the M, with lambda columns, where lambda usually is smaller than K, and a generator matrix G secret of our code. And then we multiply this by the column scrambler. So observe that basically, very informally speaking, the distortion matrix is supposed to hide the structure of the hidden code, which constitute the secret, a part of the secret of the private key. So in order to encrypt the plaintext then, we first multiply the plaintext by the public matrix G. And in this way, we get a code word of C pub code. And then we sum this quantity by a random vector of rank equal to tau, where tau is equal to n minus k divided by 2. And to decrypt, what we do is we multiply C by the inverse of the column scrambler P. And then we observe that thanks to the fact that P has coefficients in FQ, the rank of E times P minus 1 is equal to the rank of E, which is equal to tau. And so it just suffices to look at the last n components of this vector to get the access to the Gabidulin secret code. And so it just suffices to decode the last n components to get M times S. And then we multiply by S minus 1, and we get the plaintext M. OK, so S is not relevant. We can omit it just for simplicity. And we now talk about the Overbeck's attack. OK, so the main idea behind this attack is related to the following observation. So basically, if we apply the Q-sum operator to a random code with generator matrix C, for example, then we get this matrix lambda I of C, whose rank is full with high probability. While if we apply the Q-sum operator to a Gabidulin code, we get a Gabidulin code. And the dimension, for example, of its Moore matrix is equal to the minimum between k plus I and n. So if we choose an I for which k plus I is equal to the rank of mk plus I, for example, then we have that this rank is much smaller than the rank of the matrix lambda I of C. So the Q-sum operator basically allows us to distinguish Gabidulin codes from random codes. and to possibly construct an attack to find the structure of our hidden code. In particular, we observe that if we consider lambda I of G-pub is our public key, we get this multiplication of these two matrices where P remains unchanged because P has coefficients in FQ. And on the other part, we have another matrix which has two important blocks. So the first block in pink is the block related to the Gabidulin secret code, the code obtained by applying the Q-sum operator to the Gabidulin secret code, and a matrix in yellow X bar. We know that the rank of this matrix is bounded by lambda. Lambda is the number of columns of our distortion matrix. And in particular, if for a certain I, the rank of this matrix in yellow is equal to lambda, it means that the rank of lambda I of G-pub is equal to K plus I plus lambda. And so the dimension of the Q-sum operator applied to the public code is equal to K plus I plus lambda. So the dimension of the dual of this code is equal to n minus k minus I, which is exactly the dimension of the dual of the Gabidulin code obtained by applying the Q-sum operator to the hidden Gabidulin code. So in other terms, it means that the Q-sum operator applied to the code, to the public code, has a parity check matrix of this form. So in a certain sense, we managed to remove the part of our public key related to the distortion matrix and to get the access to our Gabidulin secret code. And in particular, so we have this equality, and in particular, Overbeck proved that any invertible matrix with coefficients in FQ, which multiplied by a parity check matrix of the Q-sum operator of C-pub, gives us a block of zeros in the beginning, is what we call the valid column scrambler, meaning that this matrix T behaves exactly in the same way as the column scrambler P. So once we find such an invertible matrix, then we win, because it just suffices to decode the last n components of the ciphertext times T minus 1, exactly as we did before for the decryption phase, to find the plaintext. And it's here that the remark that we did in the beginning, it's useful, because if we needed the evaluation sequence to decode, before, between the last two steps, we needed to recover G to decode. But since we don't need to decode G to recover G to decode, we just need a generator matrix of our code, we can make the attack more easier. So we can skip this step. And we can just decode the last n components of CT minus 1 to get the plaintext. So basically, the Overbeck attack consisting in finding an I for which the rank of this matrix in yellow is equal to lambda, or equivalently, the dimension of this dual is equal to n minus k minus 1, minus I. Then we find an invertible matrix, which multiplied by H-pub gives us a block of zeros, and then we decode the last n components of CT minus 1 to retrieve the plaintext. Now, if for I equal to n minus k minus 1, we have that the rank of the yellow matrix is equal to lambda, it means that the dimension of the dual is equal to 1. And so the dual of the Gabidulin code with dimension k plus I is equal to 1. So it means that in this case, the attack is simpler, because it just suffices to find a valid column scrambler, an invertible matrix, which multiplied by H give us just a vector with some zeros in the beginning to implement the attack, to attack the system. Many papers in the literature claim that this is the Overbeck attack. They say the Overbeck attack consists in just verifying if the dimension of the dual of the Q-sum operator applied to the public code with I equal to n minus k minus 1 is equal to 1. But this is not the case. The Overbeck's attack, as we have seen before, is more general than that. Okay, so let's now talk about twisted Gabidulin codes to then describe the twisted GPT system. So in order to define them, we need a special class of Q polynomials of bounded degree bounded by K. So we fix a certain number of twists, so for example 2, and we consider the first K-1 monomials, and then in correspondence of two integers, h1 and h2 of 2 powers, we consider other 2 monomials corresponding to the power k-1 plus t1 and k-1 plus t2, where t1 and t2 are chosen in a certain way. So basically, linear combinations of such monomials is what we call twisted Q polynomials. Twisted Gabidulin codes, we can generalize this construction for a general number of twists. And twisted Gabidulin codes are the evaluations of such twisted Q polynomials of bounded degrees. And what happens if we apply the Q-sum operator to such codes? We lose the structure of twisted Gabidulin codes, so we don't have neither twisted Gabidulin codes, neither Gabidulin codes. But we have some codes whose dimension is equal to this quantity here. So it's the dimension we observe that increase faster than the dimension of the Q-sum operator applied to classical Gabidulin codes. And it's something which depends on the parameter L, which is the number of twists. And we can observe that even if the dimension is bigger than the previous case, it's for special choices, for some choices of I, this dimension can be smaller than the dimension of the Q-sum operator applied to a random code. So we can get an intuition that basically we can have a criterion to distinguish even these kinds of codes from random ones. But nevertheless, in their paper of 2018, Puchinger and Vectorze proved that this kind of system, so the twisted GPT is just GPT where we replace Gabidulin codes with twisted Gabidulin codes, is resistant to the Overbeck's attack because they show that they choose some parameters for which the dimension of the dual of the Q-sum operator related to I equal to n minus k minus 1 is always different from 1 for such parameters. But we have seen that it's not sufficient to say that this system is resistant to the Overbeck's attack, because the Overbeck's attack is more general than that. And another problem of their proposal is that there exists in the literature any decoding algorithm for such codes for more than one twist, which correct up to the alpha of the minimum distance. So one of what we do in our work is that we also apply the same exactly algorithm that we apply for Gabidulin codes to these codes, but unfortunately we can't correct up to the alpha of the minimum distance of the code. We can correct less. And we prove that we can apply exactly in the same way as for the classical GPT system the Overbeck's attack, because we observe that the Q-sum operator applied to the public key splits into 2 matrices, where the matrix in yellow has a rank which is bounded by k, and in particular we can apply the attack if we find an I for which this rank is equal to lambda, exactly in the same way as before. We also extend the Overbeck's attack in the case in which the yellow matrix, so the matrix of the X tilde, for example, has a rank smaller than lambda. And we prove that basically we can apply the attack and we can extend the attack for any I for which the lambda I of G cubed splits into 2 blocks of this form. It's quite technical. It just suffices to look at a specific set, which is an algebra, which is an algebra structure, which is the set of matrices with coefficients in FQ, which multiplied by code words of the lambda I of C cube code gives another code words of the same code. And In particular, we can prove that this algebra contains these two special matrices which form what we call a minimal decomposition of the stabilizer of the first algebra into orthogonal idempotents. It's quite technical, but I want you just to convey the idea. So E1 and E2 are idempotents because they satisfy these two equalities. And they form a decomposition into orthogonal idempotents because they are orthogonal and because their sum is equal to the identity with n plus lambda, corresponding to n plus lambda. And in particular, we prove that any minimal decomposition contains a unique matrix, which F, which has rank equal to n, which is related to E2. And this matrix plays exactly the same role as the column scrambler. So it's a valid column scrambler. So, very shortly, the idea of our attack, we first find an I for which this matrix splits. We then compute the stabilizer algebra. We compute the decomposition of the stabilizer algebra into orthogonal idempotents. We search for special matrix F, which is related to the matrix C2. And we decode, and since we know that this matrix behaves exactly as the column scrambler, we decode the last n components of C times F to retrieve the plain text. And just a quick view in terms of operations. The computation of the stabilizer algebra, it's just linear algebra. And in order to compute this minimal decomposition, there is an algorithm which is described in these two papers. But we prove that we can simplify this algorithm by using the fact that here we are in a very specific setting. OK, so let's draw the conclusion. So what we have seen is that basically we revisit and extend the Overbeck's attack. And we apply this version, the classical version and the extended version to the Twisted GPT scheme. So thank you for your attention.
So thank you, Ilaria. We have time for one or two questions. Anyone? Okay, I have a small question. I noticed that in the parameter example you give, most of the time you have always you have two twists.
Yeah.
What would happen with more twists? Is it more secure? Is it possible to build a scheme, etc.?
Is it possible to build a scheme? In terms of security, we choose these parameters because these are the parameters that are proposed in the paper of Twisted GPT, so we applied the attack for this. But in theory, we can apply the attack also for a bigger number of twists. Yeah, without problems. We choose these ones because the paper that we decided to attack choose these parameters.
Okay, the attack works the same way?
Yeah, it works in the same way.
Yeah,
yeah. There are things that needed to pay attention with. For example, we have to choose I for which the dimension of the QSUM operator applied to the code is not too big, because we needed to have the attack, but the attack is supposed to work even for this case.
Okay, thank you. Anything else? Okay, so thank you again.
Thank you very much.